Welcome back. This is Lecture 7b, Quantum Compilation, Solving the Routing Problem. I'm Jonathan Baker. In today's video, we're going to cover the routing problem for quantum compilation. What is this problem? What are the objectives? And then discuss some simple strategies for how to approach and solve this problem. In the past, we've talked quite extensively about how communication costs are prohibitive on near-term devices, or requiring us to add lots of additional operations in order to execute our input program. So let's see our small example in that our input program here on the left. We have maybe qubit A interacting with qubit B in the C0 gate. And we've compiled it, or we've mapped it somewhere on the hardware. So we have our hardware here. Let's say it's this 3x3 grid. And for some reason, we've mapped poorly A and B to the edges of the device. And so we have these intermediate qubits. Let's call them C1, C2, and C3, for example. And then our compiler here in the middle has to add in additional operations to actually execute this operation between A and B. So now we have this program between C2 and C3 and B. And in this device, maybe we swap to move things. So we'll have to move through these swap operations to these intermediate qubits along the path from A to B in order to execute the desired gate between this whatever qubit A is and qubit B is. So we've added these extra swaps here. This is the communication cost. We'll just call it communication here. So the reason that we have all these extra communication operations is from the fact that near-term devices have limited connectivity. So this device, the hardware graph in the top here, has only certain allowed operations, or you can only execute 2 qubit operations between certain pairs in the device. In fact, the hardware graphs are typically fairly sparse, even if there are some regions that are really well connected. So if we had an ion trap, for example, we saw that the traps themselves could be really well connected, but there might be loose connections or sparse connections between the traps themselves, which would lead to maybe an overall average of higher sparsity. There are very few examples outside of the very small prototypes that have all-to-all connectivity, meaning that we could interact freely without any of this extra communication between any pair of qubits on the device. So in our model, we're working under these sparse connectivity graphs, hardware graphs. And so in order to communicate qubits at a distance, we need to perform, which we're required to perform the written operations. So we wrote the C0, but we had to execute all these extra things. So we have to do something in the form of movement. And in this case, we use swaps, but you could use something like a move, like physically moving the qubits in an ion setting, or something else. The dominant approach is, of course, this swaps. And in even cases where there is movement, there might also be some logical swapping that needs to be done. So we would still maybe swap the states of physical qubits using a swap. But let's just remind ourselves for the future what this swap thing is equal to. It's a sequence of 3 C0s in our basic components. Most hardware doesn't actually give you access to the swap itself, and instead asks you to write it in terms of more basic fundamental gates. So by performing chains of these swaps, or whatever movement we've done, we can effectively transport the states of qubits from one side of the device to the other. And this is, for the most part, required. There's not going to be a way around this. Okay, so what exactly is the routing problem? There are several formulations. The first would be given some state of the device. So say, for example, we're in the starting state up here, where we've probably first mapped it. And we have some new state that we want to go to. Say, let's write a new picture down here. We want to go to a state, some new mapping, where A is now located next to B. We've made an arbitrary choice to move A to B, but we could have done something else. But this is the state that we want to. This is the target state. And the question is, what sequence of actions can I take on the input that will quickly and accurately get me to the target. Of course, again, whatever means, quickest or best is going to depend on different objectives that we might set for ourselves. We could also ask a different question. Given the current state of the device, what is the next best state for the device? So instead of having decided that A goes next to B, we could ask the question, where should A and B be? Should it have been like this, or we'll call this A and B prime, or maybe something like this? And so of all the possible states that we should go to, which one should we go to? And of course, that's a much harder problem than if I just decide that A should be next to B. There's a lot of possible remappings. As we saw, mapping itself was hard. Then choosing amongst all the mappings for the next best one would also be hard. Of course, we could also ask a much more global question, that if I have some input program to execute, what is the minimal amount of communication that's going to be required to execute the whole program on the device? So at every step, we know that interacting qubits will be adjacent on hardware, and what are the total amount of communication operations I'm going to need to use to achieve that. That, of course, will be hard as well to know that. Okay, so let's talk about some objectives that we might set. We've talked a lot about the term communication cost. I even almost wrote it here at the beginning. But let's try to set some high-level metrics for what we want to optimize over so that we can actually design some heuristics. The most natural we've talked a lot about is minimizing the length of the path between two interacting qubits. So when the length of the path is long, so for example in our hardware graph, let's just rewrite the graph so we can see it more clearly down here. There are, of course, many options to move A to B. We could have taken some roundabout path through the device. And of course, when I wrote it up here, I took a shorter path that was more direct towards B. That ended up taking fewer operations. And when we talk about distance, we're talking about distance in terms of the graph. So if we are assuming all of these edges have weight 1, then it's just the total. Like we want to minimize the total number of edges in the path itself. Physically, it doesn't necessarily relate to their physical locality. For example, in an ion trap, the two in a globally connected trap, even though they're physically very far away and there may be many qubits between them, in their interaction graph they're connected, so that would still be a short distance between them. Okay, so while path length is usually a good target to minimize, we might have many possible different paths of equal length that we might. So we might want to talk about some other objectives so that we can differentiate between the paths. For example, we might want to choose swap paths which maximize our ability to parallelize. So if we have two paths, one that intersects a lot of frequently interacting qubits, that might actually hinder our ability to parallelize and execute those operations at the same time as we're swapping around them. In the same vein, we might want to choose paths which themselves can occur in parallel. So say we have C and D that also want to execute, then if we choose a path that intersects a path from C to D, then this might be a problem. So we might want to parallelize the two paths in a way they can both execute at the same time, so that we minimize the execution time of our program at the same time as minimizing the total extra operations that we add. Finally, we may not have a uniform device. The error rates or gate durations for different links in a hardware graph can be different. And so we might want to modify how we choose our paths based on either error or total program duration, etc. As you can see, there's a huge number of variables and many more we didn't cover that are device specific that we need to consider these when attempting to solve the routing problem, and doing so is critical to program success. If we ignore the fact that gates are high in error and we just choose ones that are short in duration, then we may end up adding lots of extra gates that we don't need, or choosing paths that are inherently longer or more error prone. So we need to also think about what are the best objectives given our current device. Many of the other compilation steps we've discussed up to now, synthesis, mapping, scheduling, optimization, are all contingent on our routing techniques being efficient. Let's give some intuition for this. Suppose we have a program and we send it through all the other optimization steps. And the compiler spits out this really nice looking program. Like it removed a bunch of the 2-qubit gates, it parallelized, it made sure that gates were going to execute quickly, and the total program is going to be short. But then suppose we just throw out some basic mapping and routing techniques at the circuit. Say we're compiling to the same 2D mesh architecture. The routing methods could result in a huge communication cost overhead, something like square root of n in the size of the grid. And if always taking, even if we're always taking the short paths between interacting qubits, that's going to be really bad for our circuit. When the goal of current algorithms is to push the size of programs we can execute, we need to squeeze out of the device as much as we can and not waste it on non-computation operations like swaps and moves. Because of this, there's a lot of research in this area, and I'm just going to skim the top of it and give some intuition and ideas about how we can solve this problem effectively. Okay, so let's discuss some of these basic strategies for routing. These don't necessarily scale well, but give an intuition about the complexity of the problem. You should just start with something simple solution and then think about what goes wrong with that solution and how we can improve it. The first is the swap there, swap back method. This seems really expensive at first glance, so let's see what it is. So we're going to keep using our example of being on a 3x3 grid. Oops. And we have, say this, it's not poorly mapped, but we need to, for some reason, interact A and B. There's a C0 between them, and so we have to move them adjacent. The idea here is that we swap 2B in the forward direction. So we're now A is kind of temporarily located here. We can execute our C0 between A prime and B. And then when we're done, we're just going to swap it back. So it'll be the squiggly arrows. We move back to where we started. We can use the same path, we might use a different one, but the idea is that A is then returning to its original location. So this clearly seems really expensive. If we just moved A to B and then stopped and executed the gate, then that was great. We used about half as many swaps. And for the most part, that's true. It's expensive. But let's give some intuition of why this might be a strategy we want to use. Say we have a really good mapper. It always places frequently interacting qubits together in tight clusters. However, occasionally those qubits need to interact outside their clusters, the keyword being occasionally, only a few times. And even if these interactions are far away. If we move the control to the target, there's no specific reason, you can choose the other one, but for this example and for future examples, we're going to assume we always move in control to target. And our C0 gates, then after we finish the C0, our control is going to be far away from its tight cluster. So we're assuming that A may be all of these qubits around A. We'll call them C1, C2, and C3. We know that A is going to interact a lot of times with C1, C2, and C3. Then putting it back into its original location is going to be really beneficial because we know then it's a short distance from all of its other frequently interacting qubits. So even though we have to sometimes move it far away, this swapping back guarantees that it's never too far away from other qubits in its cluster. We can imagine a much bigger device, we'll just draw it as a square, that we moved A across the device to B, and now it's really far stranded away from. So in the smaller example, it's not that clear that it's that far away from other qubits. But here, maybe it only interacts in this upper left corner a lot. Then moving it out is now left a lot of movement back to other qubits there. Or worse, it actually draws the qubits that it's interacting away from that cluster too. So then it's breaking up this really well mapped tight cluster. Okay, so the swap back method does have some merit to it, but it really depends on the structure of the input program and the hardware, of course. Okay, so yeah, this is working best when a program is well clustered and divided into these regions of heavy computation, like this dotted group on the right. This strategy can be effective and competitive with other strategies, but is not often the case, as our intuition tells us that we're doing a lot of swapping back, potentially. And it also, yeah. Okay, so a simple modification to this strategy, which can be highly effective, is to instead of moving the control to the target, or the other way, we instead meet in the middle. So we'll redraw our example. And we have A and B, of course, interacting. And instead of moving A all the way to B, we can simultaneously move A to B. So then we're parallel, even though we're going to use the same number of swaps, since the distance between A and B is the same, we can parallelize this. We can do this first swap from A and this first swap from B at the same time, and then after one more step, we can execute the C0 between them. This doesn't really have all the same advantage because maybe we still are swapping back. So we're going to still spend the same number of gates, but it does parallelize a little bit better. So we can start with something simple and then make modifications to improve upon it. Okay, finally, let's consider one other strategy, which is maybe the one that you've already thought of as an adjustment to what we just did, which is to swap there and then stay there. So our same example is we move A along the same path, and now A is just located here. When we're done with the C0 between A and A prime, at a location A prime and B, then we're just done. The mapping has now been modified from this swap path. And then in future interactions, we would just consider where is A now? A is located down here, and if we need to move it again, we'll just do that. Obviously, in the previous examples, keeping qubits in a fixed location isn't entirely practical, as it assumes something very particular about the structure of a program. In the previous video, when discussing the program interaction graph, we simply weighted edges. Yeah, so let's revisit our idea of the interaction graph. We had some graph, and we weighted each of these edges by the number of times that they interacted. Say this is the number of times. This strategy was good for seeing that, okay, say A and B interact really heavily, and A and C interact really heavily, but C and B don't necessarily need to be close to each other because they only interact twice. Whereas on the other hand, C and D might need to be frequently connected or interacted, so they should be located closely. Okay, but this representation neglects the really important aspect of time. So say, for example, A and B interact really heavily at the beginning of the program. So let's just draw a block diagram for our circuit. And say in this first part of the circuit, A and B heavily interact. They need to be close together because they're interacting like every other step. But in the middle, they don't interact at all. So it's like no A plus B. But at the end, they again interact heavily. So this program graph on the left will say, okay, look, A and B interact really heavily because over the entire course of the program, there's lots of interactions between A and B. But it's not quite true that they need to be together at all times during the circuit. And instead, during the middle, they may need to be actually relocated to other things they interact with frequently. So say all of these interactions between A and C are occurring in the middle. Then we might want to relocate A and C to be right next to each other so they can quickly interact. We've seen examples of this in practice. If you can recall some previous videos, there was the example of the Kokaro adder, an arithmetic circuit. And qubits really interacted in groups at the beginning and at the end during the uncomputation steps. And in the middle, they weren't interacting at all. Instead, they might be interacting with other qubits. So this information about time locality is completely lost when looking at the program interaction graph. And our static mapper that we've written has made a choice to map these qubits very close. And if we keep returning to that position or expect to be anchored by that position at all times, then it may actually result in a lot more frequent transportation during the middle of our program. And it might have just been better to approach the strategy on the right, which is just to move the qubit, execute the desired operation, and then leave it, and then reconsider for the next time step what's the best course of action. This reverts back to our framing of the problem as what is the next best state, for our program, and how should we get to that state in the best way. Taking advantage of this time locality is of course going to be more expensive than just looking at this static interaction graph. But it can result in huge gains, or I guess losses in this case, for the number of gates. In this way, we can think of dividing the program into many steps instead of just one giant conglomerate, and thinking about how we can adjust the mapping at each step to more favorable mappings in the next step, considering only future interactions. This kind of look-ahead procedure is common in current compilation methods and can be effective, very effective in routing. Okay, now that we have a few simple strategies we can use when designing our routing techniques, let's talk about how to choose the paths. So we've talked a lot about, if we already knew the path, how should we approach it? But how should we actually do this transportation? One of the simplest ideas is to take our graph and then just pre-compute all of the shortest paths in the device. Computing all pairs shortest paths is easy, so we can just store all this information beforehand. And then when given an option to choose moving two qubits together, we can just query this this dictionary or whatever we have for what is the shortest path, and then we'll just move along that shortest path. This seems all good, but in practice, it's sufficient for small and medium-sized programs, but it doesn't count for all those other objectives that we've mentioned before. So first, what happens if there are many shortest paths? We've seen in the grid architecture, I'll just draw it as a square now, just draw it as an actual grid, that there's many different ways to move. If I take 2 points in the grid, then you can see that there's many possible paths between 2 corners of any rectangle using the grid. We can go along the x's, we can go along the exclamation points, or etc. There's many different ways to get from one point to the other. Okay, so how should we choose between these paths? If we let a generic pathfinding algorithm choose all of our paths, we may end up with lots of intersecting paths all requiring the same qubits to be used, which will result in lots of congestion, so which will increase the execution time and therefore more error in our circuit. We could instead store all the shortest paths between nodes, and then when given an option to choose that path, choose the path that adds the least amount of disruption to our circuit. Say the one that has the best parallelism with other operations that can also be executed in that time step. So let's consider an example on a bigger grid. Let's do I'm not sure how big this is. I think a 5x5 grid, and we maybe have this point, and maybe we also want to execute gates between the x's at this time step. So this one and this one want to execute. But we've decided that we're going to do a swap path through these qubits to get between these two solid circles. This may not allow, if we choose a bad path, we may end up having to intersect these other parallel operations at the same time. So instead, we maybe should have chosen a different swap path, say around. Let's go around these gates to get to our target. Maybe this isn't the shortest path, but we can imagine in situations where there are shortest paths that don't intersect are also parallel operations. So in this case, in this first case, we might have to wait for our simultaneous operation to occur before we can swap through them, or these other simultaneous operations will have to wait for us to swap through. In either case, we're adding extra delay that may not be necessary for our circuit. Okay, second, we should ask the question, what does it even mean to be a short path? In the case where we consider a uniform target architecture, which we've done for this whole video, and by that we mean every edge behaves exactly the same when executing gates between the qubits. All these paths then are equivalent in length. They all have the same number of gates as we move through them. This uniformity assumption isn't necessarily a good one. Gates may have different execution times based on the edge, or may even have different probabilities of error. We'll cover this more in more detail in future videos, but we could adjust our paths to account for some of these parameters. For example, we could weight each of the edges by the probability of success for the gates on that edge. And of course, if we wanted to change this as a product, we'd have to do some adjustment to these parameters to make them be able to find the shortest path as some additive thing. And so then after we weight all these edges, we can just recompute what it means to be short. But this also comes with another issue, that if there are some really good edges in our device, then all of the shortest paths are going to use those same really high weighted edges, or I guess in the other case, the low weighted edges, because we're looking for shortest paths. But the best edges are going to be used in lots of different paths. And so if we want to simultaneously swap across the device, all of them are going to try to use the same edge, and that's going to cause a problem. Lots more congestion. Okay, we can see that there's a lot of different objectives and a lot of different strategies, and trying to balance all of them together results in lots of choices that we have to make. And so designing an optimal routing method that solves all these problems is really hard. And instead, we usually just pick a few good heuristics, and in practice, that's usually sufficient. But there are always people competing, lots of research trying to find the best routing methods for current devices. Okay, so let's finish by talking about a few other ideas in the routing optimization space. First, let's consider devices where our program doesn't fill up all of the available qubits. So how does this affect our routing? So let's take our same canonical 3x3 grid, and say we occupy A, B, C, and D in this circuit, and maybe E, for example, in this top left. For some reason, we've mapped it away from the other qubits. So we've not filled up all the device, but there are still these other hardware qubits available to us that we might be able to use. In many cases, the fact that we didn't fill it all up doesn't mean anything. If all our programmed qubits are mapped really tightly together, then we're just going to swap as normal. We might swap C through A and A through B, and so we're swapping our different states through each other to get where they need to go. However, in some cases, this can save us a few gates. So we normally think about those swaps, as we talked about before, as that sequence of 3 C0 gates between the source and the destination. But if we know that one of the qubits is an ancilla, or a zero state, so this is with just an arbitrary A and B, but if we know that it's A swapping to 0, some known empty state here, then we don't need to do some of the operations, and we can instead just do two of the C0s. Back. So this means that we're able to save some of our qubits, or some of our gates when we get to this point, if we have to swap through them. So for example, if A needs to swap to E, then swapping along this path is actually really efficient. Let's maybe even add an F here. So then this left path is more efficient than going upwards, this squiggly path, to E. Because in F, it might be some other state that we need to do a full swap sequence through, versus to the left, to this 0 bit, we don't need to do that. So this, of course, will change what it means to be a shortest path. And so we should make sure to prefer to use paths that use these unused qubits if possible. Because it also means that there's not an extra gate happening on this F state, whatever this F qubit is, which would mean more error. But we don't necessarily care about what happens to this 0 bit, this unused qubit. It may also even help us route for parallelism. If we can go around the outside, say in this case, then we might be able to, in parallel, do some operations at the same time by slightly extending the length of the path, but it ends up still being the same number of gates to go a little bit outside of our circuit. Okay, finally, let's consider the idea of teleportation. We've seen teleportation before, and the idea is that using an EPR pair and some classical control, we can transport the state from one qubit to another. And we can envision some hardware devices that make use of teleportation to increase the connectivity or the density of connectivity in their devices. Okay, so suppose at the beginning of our circuit, before we execute our circuit, we prepare a bunch of these teleportation pairs and we distribute them across the device. So we're going to front load a lot of communication by adding swaps to move these qubits across the device. And then when we're actually choosing a swap path in our final circuit, we may be able to take advantage of these teleportation points to quickly get from end to end of the hardware. These, of course, are one-time use, so we need to use them wisely. The hardware graph with the teleportation points, so right when we start a circuit, will be much more densely connected, but as the program executes and uses them, it'll become more sparsely connected. So there's definitely some ongoing research in this area for those that are interested. Okay, in today's video, we've covered a high-level view of the routing problem and basic strategies and objectives. This is just the start. There is so much going on in this area for optimizing communication overhead because it's so important to the success rate of programs.